Hello students, welcome to lecture 54 of the online course on the introduction to microwave and optical metamaterials. Today's lecture will be on electrically tunable metamaterials. So here's the lecture outline. We'll give you a brief introduction of electrically tunable metamaterials, and then we'll discuss graphene-based metamaterials. We'll go into the details of a graphene-based polarizer which is electrically tunable. Then we will discuss about varactor diode based metamaterials and liquid crystal based metamaterials. So in the previous lecture we have seen magnetically tunable metamaterials. Here we will be using electric field for tuning the metamaterial properties. So the topic is electrically tunable metamaterials. So these are basically a class of metamaterials whose electromagnetic properties can be actively or dynamically adjusted by changing some external electric signal or voltage bias. Now this tunability will allow for real-time control over how the electromagnetic wave basically interact with the material. So what is the benefit? It allows dynamic reconfiguration of the device behavior during its operation. So the core principle here is to integrate active electrically sensitive materials into the metamaterials structure, so that when you change the electric field during its operation, it can behave differently. So in this kind of metamaterials, applying a voltage bias or a variable voltage bias basically alter the electromagnetic properties of the active components. So this kind of alteration can lead to either the change in the resonant behavior via the change in effective permittivity or permeability. So this is what we mean by tunable electromagnetic properties. Therefore, real-time tuning of the metamaterials electromagnetic response is possible by this kind of external electrical signal or bias voltage which is being applied. Now, what is the key advantage? Why we need to do all this? So the ability to tune metamaterial properties electronically basically offers several benefits, which includes the first, response time. That means the changes can be made quickly, making them suitable for high speed applications. Another important aspect is low power consumption. So electronic control is often found to be more energy efficient as compared to other tuning methods. And then finally the compatibility. So this can be seamlessly integrated with the existing electronic control system, so that way this electrical or electrically tunable metamaterials are more compatible. So there are three types of electrically tunable metamaterials based on the materials being used. The first one is graphene based metamaterials, the second one is varactor diode based metamaterials, and the third one is liquid crystal based metamaterials. Though this is not an exclusive list, there can be different other types of metamaterials which are electrically tunable, and that is an ongoing research area. So the applications include making tunable filters and absorbers, designing reconfigurable antennas and lenses that operate at different frequencies, then modulators and switches, and also dynamic beam steering. It can be also used for adaptive cloaking. So if you think of invisibility cloaking, that basically make an object completely invisible to an electromagnetic wave such as radar or light. When you think of adaptive cloaking, that basically dynamically hide or mask objects under changing environment or conditions. Okay. So now let us look into the first one, that is graphene based tunable metamaterials. So in this case you are basically using graphene as part of your structure, and the electrical conductivity of the graphene can be tuned via change in its Fermi level that we all know. So this Fermi level, if you put the graphene in a particular capacitor kind of a configuration, you can basically change this Fermi level by changing the applied voltage bias. So, we will show you how this arrangement looks like. So, this basically makes graphene ideal for electrically tunable metamaterials. Now, typically this kind of metamaterials work in the terahertz and the infrared frequency ranges. So, you can make graphene based electrically tunable devices such as electrically tunable graphene based polarizer. So, here is an example of electrically tunable graphene based polarizer. So, this is how it looks like in the perspective view, and this is the top view. We will come into this in details. So, this polarizer has got some electrically controllable polarization direction that can be changed by applying voltage bias across the graphene. So, what is the operating range? It typically operates in far infrared, but you can extend this to terahertz radiation regime also. So, here is the structure that we have been discussing of this electrically tunable polarizer. So, you can see it basically composed of two orthogonal periodic arrays of graphene ribbons. So, there are like X ribbons and Y ribbons, okay, and they are of different width. So, the width of the X ribbons are W2, Y ribbons are W1, and this is the periodicity, okay, that is P. Now, as you see here that these ribbons are basically placed on a dielectric film over a thick metal substrate. So, there is a thick metal substrate, and then you have this kind of metallic electrode on the top layer. So, when you apply voltage, this entire thing acts like a electrode. The bottom one is another electrode, okay, and then in between you have this capacitive effect, right. So, these are the geometric parameters which are of importance. One is the periodicity of the graphene ribbons, that is P, thickness of the dielectric material TD, that also plays an important role, and thickness of the metallic layer TM, that is the bottom metal layer that you are able to see. So, what is the operating mechanism in this case? So, based on the polarization dependent resonant absorption, okay, you will have two different because there are two orthogonal ribbon sets. So, it basically the polarizer operates based on polarization dependent resonant absorption, right. So, the absorption of each ribbon array, because they have different width, okay, so they have different absorption frequency, and that can be controlled independently by applying different voltage bias. So, how you are doing the electrical doping here? So, you can basically apply a voltage bias between these graphene ribbons and the thick metal piece at the bottom. So, here the metal substrate that you see at the bottom, that is a thick metallic plate, that serves two purposes. First of all, it acts as a back gate to electrically dope the graphene. Secondly, it also suppresses all the transmission that is going through the channel. So, whatever if the incident light is shown like this, is falling on the top, if it is not absorbed, it is basically reflected because nothing is getting transmitted. So, now we also know that now graphene in this particular frequency range also supports plasmons. So, doped graphene ribbons will also can support strong log-lived plasmons, and these plasmons will produce sharp resonances when they are excited by an electric field which are perpendicular to the ribbons, okay. So, that you can see here, this is basically the K vector and this is the electric field vector, right. So, you can estimate the first order graphene plasmon resonance to occur at W equals 1 minus phi by pi, lambda effective by 2. So, this is basically the resonance condition. Here W is basically the width of the ribbon, right. And then there are other two terms, phi. So, phi is basically the phase of the reflection coefficient at the ribbon ends, okay. And then you have lambda effective, that is basically the effective resonance wavelength which is determined from the real part of the graphene plasmon's permittivity or the refractive index that is given by N effective, real of the N effective. Okay. So, you get a new term here, effective wavelength, that is basically being calculated as lambda naught divided by lambda effective is nothing but lambda naught divided by a real part of N effective, right. What is lambda naught? That is basically the vacuum wavelength, and real part of the N effective can be estimated as h bar omega divided by 2 alpha naught EF. So, alpha naught is basically the fine structure constant, okay, and EF is basically the Fermi energy, right. So, once you know this, you can also obtain the resonance frequency. So, that you can do by substituting the expression for real part of N effective into the resonance condition that we have seen here, and that can give you the resonance frequency F, which is estimated as square root of C, that is basically the speed of light in vacuum, times alpha naught, which is the fine structure constant, EF Fermi energy, and then you have 1 minus phi by pi, the whole thing divided by 2 pi h bar into W. So, h bar is nothing but the reduced Planck's constant, okay, and all other terms are already discussed. W is basically the width of the ribbons. So, this equation basically shows direct relationship between tunable Fermi energy and the resulting resonance frequency. So, that is something very interesting. Okay. Now, this equation also tells us that the resonance frequency of the graphene based structures are tunable. So, if you just change the Fermi energy by adjusting the voltage, gate voltage as shown here, you can change the resonance frequency. Also, you can change the width of the graphene ribbons, that will also change the resonance frequency. So, in this design, suppose a monochromatic linearly polarized plane wave is normally incident on this particular system of two orthogonal graphene ribbon arrays. Okay. So, you can write the incident wave in terms of this electric field incident, which is nothing but cos theta x cap plus sin theta y cap into e to the power minus I 2 pi f naught into t. So, f naught is nothing but the plasmon resonance frequency, or you can say the operational frequency, and theta is basically the polarization angle. Okay. Now, because you have two different ribbons here, or ribbon widths W1 and W2, so you can correlate that f naught will be equal to EF1 and W1 for the first ribbon, and for the other ribbon it will be the Fermi energy will be EF2 and the width will be W2, remaining all parameters remain same. So, what does it tell you? That you can say that your resonance frequency is basically proportional to square root of Fermi energy by width ratio. Okay. So, you can write square root of EF1 divided by W1 will be equal to square root of EF2 by W2. So, this tells you that the resonance frequency basically depends on both Fermi energy as well as the ribbon width, and this condition also confirms that the resonance can be maintained to the same frequency by adjusting the Fermi energy to compensate for different ribbon widths, because in this case we are taking W1 and W2. So, EF1 and EF2 need to be correspondingly adjusted, so that you still get the same resonance frequency from the two different nano ribbons. Okay. Now, from the incident electric field, you can decompose that and find out the field that will correspond to TM mode and TE mode. So, you can consider Ex incident to be equal to cos theta x cap e to the power minus I 2 pi f naught into t, that will correspond to the TM mode, and then on the other side you can write Ey. So, these are basically the electric field along x and y that corresponds to TM and TE mode respectively. So, Ey in will give you sin theta y cap e to the power minus I 2 pi f naught into t, So that is basically the TE mode. Okay. Now let's consider in the first case that the Fermi energy is EF1. So in that case, what you will see that the TE mode, which is basically the Y component, that will exhibit the plasmon resonance in W1 width ribbon. So in that case the energy will get absorbed, and the TM mode, which is basically the X component, okay, will not show the resonance. In that case the energy will be, incident beam will be reflected. So the reflected polarization is basically coming from the X direction. So the structure basically functions as a X polarizer, right. Now if you consider that you have set the Fermi energy to EF2, so what is happening, the reverse will happen, that your TE component, that is basically the Y component, will now be non-resonant, so it will get reflected, whereas the TM component, that is the X component, will excite plasmon resonance, so it will get absorbed, okay, in the T2 width ribbons. Fine. So what you are seeing, that the reflected polarization is basically the Y polarization, and that means this structure is now performing as a Y polarizer when the Fermi energy is set to EF2. So the simulation results also confirm the same. So here you see the absorption spectrum, here you see the corresponding reflection spectrum. So you can see the absorption is basically achieved. So these are two different bias voltages and for the corresponding polarization modes which are shown, okay. So it is clearly seen that the polarization direction can be actively switched by changing the Fermi energy level, and as you see here, as the Fermi energy is increasing, the absorption frequency also rises rapidly, okay. So you can see that the energy is also moving to higher energy levels. So here what are the two Fermi energies considered? One is 0.535 electron volt, the other one is 0.6 electron volt. Okay. So what we achieved here? We basically achieved a electrically tunable polarizer using orthogonal graphene ribbons. So one thing you can cross check, that whenever there is a strong absorption, that is also giving you a reflection dip, because what is getting absorbed is not getting reflected, and transmission is 0 because of that thick metallic plate as a substrate, right. So this you can correlate, this is the Fermi level and the polarization of the beam, right. So this is how you can make a electrically tunable graphene based polarizer. Now let us move into the next application, that is varactor diode based metamaterials. So here we are discussing electrically tunable metamaterials which are based on varactor diodes. So we will take an example here, which is a tunable microwave metamaterial absorber that is designed using split square loops. As you can see here, this metallic loops with two splits, okay. So you are basically placing varactor diodes in those gaps, right. So in this design, varactor diodes are basically embedded in this split square loops or SSLs, okay, of the metamaterial absorber. You can see the structure carefully. This is a copper loop. Below this there is a FR4 substrate of thickness D, and then you have a copper ground plane on the other side, okay. So this is the direction of the wave incident, and then this is the electric field and magnetic field direction, right. So you are considering the two varactors under TE wave illumination, right. Now what is varactor diode? It is basically a semiconductor diode based on the principle of variable capacitance between PN junctions, right. So in this diode you can have variable capacitance which is controlled by the applied voltage. So when you load them into these split square loops, they can basically alter the resonance characteristics. So this structure basically shows a compact planar, okay, and a simple feeding network. So it is designed as a metal dielectric metal kind of structure, and it has got a copper ground plane that ensures zero transmission, right. So now let us look into what is the effect of these varactors on the split square loops. So for that you have to compare the SLL's behavior with and without varactors, right. So let us use equivalent circuit model for this metamaterial absorber, and that will help you to compare the two cases. So this is the RLC equivalent RLC circuit model that can be used for the case without any varactor. So this metamaterial absorber can be treated as a medium which has got a frequency dependent impedance Z omega that you can see here. So that can be obtained from square root of mu omega divided by epsilon omega, and then this is the free space impedance, or you can say impedance of free space. The value is around 377 ohm, all of you know that. Now, so what will happen, because this is an absorber, so the maximum absorption can happen when this Z omega will be equal to Z naught. So that should happen at the resonance, right. So because you have also incorporated a copper ground plane which can block transmission, so whenever there is impedance matching, that means maximum absorption will take place, and that will also ensure minimum reflection, right. And you also have a grounded FR4 layer which act as an equivalent inductor, okay, and you can model it as LD due to the thin thickness. So this is how the loop is modeled. So you have the inductance, you have the resistance, and also the gaps are modeled as capacitors, right. So in this case, okay, normally the resonance frequency of this RLC loop can be obtained using this formula. So you can write FR equals 1 over square root of FR equals 1 over 2 pi square root of L plus LD into C, right. Now when you act a varactor into those gaps, so the capacitance from the varactor will appear in parallel with the capacitance here. So what is happening, the overall capacitance basically increasing. So if the denominator increases, your resonance frequency will come down. So it basically lowers the resonance frequency, right. And the capacitance C, this one, is basically determined from the size of the split of the loops, right. Now here you can see that this is depending on the size of the loops, and this is CV, which is the capacitance of the varactors. That can be determined using this equation. You can consider CV equals C naught 1 minus VR by VR whole to the power minus m. So this is basically a voltage dependent quantity, okay, in this resonance equation. So here VR stands for the reverse bias voltage. C naught is basically 2.35 picofarad, which is considered as the zero bias capacitance. You have this m, which is basically considered as 0.8, that is the gradient coefficient of the varactor, and then you have Vi, which is basically the intrinsic potential, and it is taken as 1.5 volt. So thus you can see that when you vary the external voltage, okay, an active metamaterial absorber can be designed using varactors, okay, because this value will change, okay, and that will change the resonance frequency of the whole structure. So here are some simulation results. So the first one shows the S11, that is basically the transmission characteristics, okay, sorry, this is S11, basically it is showing the reflection coefficient, okay. So this basically shows the reflection coefficient of the square split square loops, okay, without and with varactors. So without varactor, you can see the resonance frequency is around 11.23 gigahertz and the reflection coefficient is minus 8.45 dB. But when you introduce varactors into those splits, you will see that if to Zero bias varactors which have got capacitance of 2.35 picofarad, those are placed in these loops. You can see the resonance frequency basically shifts to 5.24 gigahertz, and you also see that the reflection coefficient improves to minus 13.26 dB, that is the new minimum, and lower reflection basically ensures better impedance matching. So, it is a very good thing. And this one basically shows that the frequency tunability that you can achieve between 5.18 gigahertz to 5.68 gigahertz, okay, when you are applying different voltages on the feeding network, right. So, as you can increase the voltage from 0 volt up to 12 volt, these are the simulation, and the solid one shows the experimental values, okay. You can see the shift in the resonance frequency, right. So, the role of varactor, I hope it is very clear that adding varactor is equivalent to connecting a capacitor in parallel with the inherent capacitance of those splits. So, this basically increases the overall capacitance in the circuit, and that way your resonance frequency will also decrease, right. So, that is how you can tune it. Now, the last topic that we will be discussing today will be liquid crystal based metamaterials. Now, liquid crystal properties, are very interesting. Liquid crystals are basically interstate substance between crystalline and liquid states, and they are extremely sensitive to the external fields. So, in the power on state, you will see that when the field is present, the liquid crystal molecular arrangement becomes orderly, okay, leading to some special physical properties. And when in powered off state, okay, these liquid crystal molecules become disordered. Now, it has been widely used for tuning the band gap of photonic crystals at optical frequencies. Here we will be focusing on metamaterials in the microwave range, and their nematic liquid crystal play a very important role. So, these nematic liquid crystals are basically a state of matter characterized by the molecules that exhibit long range orientational order. It means that they tend to align along a common direction, but they lack positional ordering, okay, meaning that they are not arranged in a regular lattice. However, there is a long range order, right. So, they are a type of liquid crystal which is basically a phase of matter, as I discussed, that has properties between the conventional liquid and solid crystals. Now, you can achieve this electrical tunability in the metamaterials by using nematic liquid crystal in the structure itself. So, this can be used to dynamically control the permittivity of the metamaterial, and this control allows for tuning of reversed electromagnetic behaviors of the metamaterial, such as negative permittivity or permeability. So, here is a design of a split ring resonator array being immersed in nematic liquid crystal, okay. So, this is one particular case where you have electrodes on either side to apply the biasing, voltage biasing, and these are liquid crystals, okay, where the split ring resonator arrays are basically embedded or immersed, right. So, it is understood that the structure basically consists of periodic array of split ring resonators, but these arrays are basically infiltrated with nematic liquid crystals whose properties will change depending on the applied voltage bias. So, now when you apply voltage bias, the electric field strength will increase and these nematic liquid crystal molecules will become more orderly. So, this will cause the frequency ranges of the negative permittivity to shift to a lower frequency, okay. We will see that also. So, how they are connected? So, the effective permeability in split ring resonator array metamaterials follow this particular relation, where you have mu omega equals 1 minus f omega square divided by omega square minus omega naught square minus I gamma omega. We have seen this earlier. So, F is basically the fractional volume of the split ring resonators and gamma is the dissipation factor. Now, when you calculate the S21 from this kind of a system, you can see there is a transmission dip through this metamaterial, and the black solid line shows that there are no liquid crystal put. Okay, and then as soon as you put the liquid crystals, the peak basically shifts to this red position, and this is when no electric field is applied, and later on you keep on applying the electric field biasing and you will see the dip, the transmission dip is basically shifting towards lower frequency. So, here what is seen is that maximum frequency shift of the resonance dip is approximately 210 megahertz, that is 0.21 gigahertz, and this shift is occurring related to the resonance frequency, which is around 11.08 gigahertz. Now, from this formula you can use this formula and see, here you are getting F equals 0.05 and gamma is taken as 10 to the 10 divided by 4 pi for simulation, and that will give you the permeability, right. So, that thing you can also see here. So, the black solid line shows that when there are no liquid crystals in the device, but then the red dashed one shows when liquid crystal is present but no biasing, and these are for two different biasing, right. So, what you see clearly is that the negative permeability, okay, was observed when there is no liquid crystal, that is observed around 13.24 to 13.54 gigahertz here, okay, in this region. But as soon as you put a liquid crystal but no electric field biasing, you see a very strong red shift, okay, and the new range is somewhere between 11.08 to 11.36 gigahertz, and then you can apply DC electric field slowly, and then you can apply DC electric field on this liquid crystal infiltrated metamaterials, and you will see that now when the electric field is 0.067 volt per micrometer, the negative permeability shifts towards lower frequency. It is now between 10.98 to 11.26 gigahertz, and if you further increase the field to 0.28 volt per micrometer, it further shifts towards blue, okay, or no, it's not called blue, it's towards lower frequency. So, lower frequency is basically red shift in terms of wavelength. So, you can say these are basically undergoing red shift. So, what we observe here is that overall tunability is between 10.86 to 11.36 gigahertz, and it is almost around 200 megahertz tuning range, which is wider than the non infiltrated structure. So, you can understand that this metamaterial exhibits negative permeability near its resonance frequencies. So, the frequency range with negative permeability here can be dynamically adjusted by changing the applied electric bias, which is the DC electric field, okay, and it can be widened by about 200 megahertz by the electric field. So, you can conclude that the design basically offers a convenient method of developing adaptive or tunable metamaterials, right. So, with that we conclude this lecture. So, we will continue our discussion on thermally tunable metamaterials in the next lecture. If you have got any query regarding this lecture, drop an email to this email address mentioning the course name and the lecture number on the subject line. Thank you.